Okay, you guys, not doing my hair for this, not putting on makeup for this. We're just gonna get through some notes today. So, I want you to get your guided notes. You zooming in. My daughter's helping me today. She ate one of the demos. All right, you're going to this. Okay, we'll get to that part later. And then I want you to flip to page 6. Which you don't have yours filled in yet. This is going to be long. Just breathe, be proud of yourself. You're about to be a big bad college chemistry kid. It's going to be a longer lecture, but we're going to be filling in this. So yesterday you did an activity where we were looking inside those different containers, and they are all different shapes, and you were trying to guess with the BB and how it moved around what shape was inside that container. We did that with you guys because we wanted you to wrestle and understand a little bit with what atomic scientists had to really think about. They never got to see the inside of an atom, never got to see the proton, the neutron, the electron. They only had to guess based off of other data that they collected. So that's called inference data and observations. That's what you were doing when you were trying to figure out the maze. So, it was a struggle. Now imagine you were looking in one of those containers or you're trying to guess, and I tell you, sorry, we're never going to open this one up. You're never going to know what's inside. That's what they had to experience. They never got to look inside the container. The container was the atom. So I'm going to take you through a little history lesson of different scientists or people. This would be a philosopher, and what they discovered, what their contribution was. And you're going to be filling out this sheet as we go. And I'll kind of help you because it's not organized in a way that makes sense as far as seeing it with the table. So Democritus, this really was the first time we ever came up with the concept of the word atom. So you already have Democritus on this sheet, but I'm going to do the demo here in a bit for that. But Democritus thought that just every single element, and there really in his mind was 4: earth, wind, fire. It's like the Frozen 2. What is it, Zoe? Earth, wind, fire, and
I have no idea.
air. Earth, wind, fire, air. Earth, wind, fire. I can't remember what the 4th one is, but it's in Frozen 2. But he thought everything was made of the exact same building blocks, and he did think they were made of something smaller. He coined the term atomos, and if we were to look at a Democritus example of an atom, it would be like this. I'll come to you. So are you zooming to me?
Assume.
Okay, so can you see how if we look in this beaker, every single one of these, they're not divisible any further. He didn't think there was a proton, a neutron, or electron in here. They're all exactly the same. These are all orange marbles. And he thought the exact same type of atom built everything that we saw, and everything that was on this earth. That there wasn't a special atom that made iron, and a different special atom that made copper, and a different one that made hydrogen. He just said, hey, they're all the same. It's just kind of how they organize themselves as to whether it's iron or copper or hydrogen or water or whatever it might be. So on your chart table, what I want you to do, that very first box for a demo visual, you could either draw a picture of a beaker with the same colored marbles. You could do what I did up here of have 3, actually that's what I want us to have in the model, sorry. So go back. Under the demo, I just want you to say, hey, this would be like all marbles exactly the same. Same shape, same color. Okay? For contribution, I want you to write this. His contribution was this. Atomos, which means indivisible. So put that in the second column under contribution. And then for his model, what would his model look like? That's where I want you to have this. So minus my inability to get a gray line around these, think of them being exactly the same colors. So just like these were all the same colored marbles, and hydrogen's atom looked exactly like helium's, looked exactly like carbon's. So, and we shouldn't criticize him. Look at how long ago he was here. I mean, they didn't even take pictures back then. They had to like make you be in stone. He was the first one that said, maybe what we look at, there's something smaller than what we actually see. And that was a good thing. Remember, if at any point I'm going too fast, you have the ability to push pause, and then we can go from there and you can catch back up. So that's Democritus. So 400 BC. Then we wait quite a long time, about 2,000 years plus, and John Dalton is the next guy that actually begins to think about the atom again. So now we're in the year 1700, 1800, right in that instance. And what did Dalton say? Well, he said, you know what, Democritus, nice idea that we think that they're all the exact same type of marble, the same type of atom, but I disagree. I actually think that there's all kinds of different, and I'm going to get closer. So Zoe, if you have to, or if you can you zoom in so they can see? You know, some of these are metallic, some of these are clear. I could even dump these in here too. And Dalton said that the atoms that make up iron are going to be different than the atoms that make up nickel, will be different than the atoms that make up hydrogen. Each one of them is unique. And so his contribution would be that, but for the very first column, what was the demo? It would be all different colored marbles, all different sizes. Some of these are really big, some of these are really small, but still catch that we don't break them apart. He didn't have a concept of a proton, a neutron, and electron, but he did at least say, I think that each element has its own unique atom. That's new. That was a very new thought, and probably the most modern thought of the time as far as the atomic model and his theory. So in the second column, what's his contribution is that first bulleted point, that all substances, so pure substances, we talked about this a couple lectures ago, are made up of atoms unique to that substance. So for this one, under the model, we still are purposely using the same three elements, but his difference would now be maybe this is a black marble, this is a green marble, this is a yellow marble. There is still no proton, neutron, or electron in here, but now it's our first thought of each one of them is unique, each one of them is different. Okay. Again, you've got to pause out. I'm talking faster than what you can do. Zoe, is it still recording? You had a scary look.
Yeah, it's just the Zoom is weird.
Did you unzoom? You good?
It's good, yeah.
Okay, all right. Okay, so after that comes along J.J. Thomson, and I'm going to do a couple of different things here. But as far as some demos, I'm going to demo this Crookes tube here in a bit, because that's really what Thomson played around with. And from playing with the Crookes tube, he realized that we had this negative beam of light, which made him go, how is it negative? What's going on? He was the first one who thought that maybe the atom is something smaller than just the atom. So the first one to think about subatomic particles. Him and Millikan, who is not on this paper, they end up actually getting down to finding the electron and finding the mass of that electron. So, you know, that's amazing. When you look at the year, 1850 he's born, he dies in 1940, so this is before World War II, and they're able to measure the mass of an electron. Like that's amazing to me that they had that ability to do that. And the one thing I want you to catch is really from J.J. Thomas on, so Rutherford and Chadwick, and eventually we'll talk about Bohr in several units to come. They all knew each other. Like maybe one was a grad assistant in the other person's lab. One was researching in one part in London and somebody else was researching somewhere else, but they all knew each other and they built off of each other's knowledge. Some of them fought with each other. Niels Bohr, who is not on the sheet, we'll learn about him later, he gets in a huge fight with Einstein. They have completely opposing ideas on the electron and the atom and what's going on. So Thomson, if we were to look at his model, we're going to go a little bit in different order, okay? Because, you know, for writing down some demos, I'm about to use what's called a Crookes tube. Okay, this is how it's spelled, and I'll show you some stuff with that. But here's really the big thing. He came up with the plum pudding model. I think the plum pudding was like a thing back in England, where literally it would have been like pudding, where they just literally drop plums in the middle of this pudding. I like to think of it more as like the chocolate chip muffin model, because that's much more appealing to eat. And if we were to look inside a chocolate chip muffin, and I'm just going to break this. Oh wait, this one's a blueberry muffin. I was thinking healthier. Okay, so
What?
Can you show, like, zoom in a little bit? So what Thomson would have said is all the bread part of this would just be this positive background, this positive batter basically that cooked. So he did not know about the proton, but he knew that if an atom was neutral, there had to be some positive thing that is counteracting the negative electron. Because he definitely, and I'll show you in a little bit how he could tell that the electron was negative. He said then, okay, this atom has now this first subatomic particle inside of it. Why are you laughing at me? that is the electron. That's what the blueberries would be. So the blueberries would act like the electron inside this like white muffin, this chocolate blueberry muffin part that's positive. All right. So Crookes tube, how did he play with this? Let me get it turned on. I'm probably gonna have to turn some lights out.
You gonna burn the muffin?
No, I'm not gonna burn the muffin. And I'm not gonna eat the muffin too early either, like somebody else. Okay, you got it on?
Yeah.
Are you seeing something? Let me get a light out. So what we should see right now is just a beam, a line going across, and you go, okay, well that's kind of exciting. But what does that really show? Well, first of all, this is sending electricity across, and we can even see the electricity there, that purple line. But the tube part inside there, and this is really a cathode ray tube. So you think of like the old TV. An old TV would do the same thing where you've got kind of that big deep screen. So not a flat LCD type of screen, but the older types of computer monitors. But at the end, so I've got a yardstick in my hand, and at the end of this yardstick I have a pretty strong magnet. I'm going to put the magnet near this beam, that green beam of light. And if it was just light, it would not be impacted by magnetism. Light does nothing with a magnet. But if it was particles, then it would be impacted. And so if I put this here, you can already see how we're able to bend that beam. So that's proof that it's not just light. There is particles in there. So then he began to say, okay, there really is something going on. And if he knew which part of the magnet he was putting on this beam, he would be able to tell if he put the negative end of this magnet on here and it was attracted to it, then he would know it would have been positive. But he put the positive end here and it was attracted to it, so therefore he knew that this must be a negative beam. So he knew it was a negative beam of charged particles. He eventually finds the mass of it and he coins the term electron. Okay? Now I have another tube here, and this is truly, so what you're seeing right there, that's a cathode ray tube, but I do have the real Crookes tube, and it's kind of interesting what he purposely puts at the back of this. Remember that the church and scientists didn't get along too well back then, and they were a little anxious about some of their new discoveries because people like Galileo ended up going into prison for just saying that the earth revolved around the sun. Heaven forbid. So Crookes kind of had a little bit of fun with it, and he actually put a cross in the very back of his cathode ray tube. And I'm going to let you take a look at that. Now, Zoe, you might have to actually get up and come over. I don't know where you're going to see it better. But I want them to be able to see where that shadow is. So yeah, can you see it from there or no?
Yeah.
Okay. So yeah, and then if you actually come around this way too and show it to them, they're gonna get busy. But we can see how the beam comes through here. This also told him the path of the electrons, of the shadow went behind the cross, so that let him know that we were going from a positive to a negative end, so cathode to anode. And more proof that it was a negative something, okay, negative something there. The other one showed that it was a negative actual beam of charged particles because it was impacted by a magnet. All right, go ahead and have a seat again. Let me get some lights on. Which one did we decide? This one?
I don't remember.
Are you still on record? This one?
Yeah.
You're doing a great job. Smile a little more though. Okay. Guys, be happy that your mom is not a science teacher. You might have to do this. All right, so that was Thomson. So Demos, Crookes tube, the blueberry muffin. What does he do? His contribution is he discovers the electron. And then for a picture, I want you to put this in for his model. So these little yellow things would be the electrons. And it's sitting in like this positive proton gel. It's not protons, it's just a positive gel. Okay, he does not know about the proton yet. All right, moving on to Rutherford. Oh wait, I guess we're gonna pause out and we're gonna watch. Actually, this is gonna be such a long video I will add these in later for you to watch. It's gonna be too long if I try to incorporate it right now. So there's gonna be a couple video attachments I'll put in. Rutherford, ooh, wow, let me move that up real quick. So Rutherford ends up discovering the proton. Let me see if I can pull this up, just so it's easier to find. All right. And I think I'll also put in a link that you can get a little feel for what this gold foil experiment was like. But basically, I'm gonna let you watch the video. I think if I try to explain it, it's gonna take too long and be frustrating. But through this experiment, which was just a phenomenal experiment that he came up with, he ended up discovering that there's the proton. He does not discover the neutron yet. He said that this proton is gonna be housed in this thing called the nucleus. And this is where my daughter ate my demo. So I gave bad directions. I told her she could eat it, but I meant like eat it after I do this. Think of Hostess cupcakes. If you remember, like if those Hostess cupcakes, Zoe, what was inside in the middle of the cupcake when you ate it? What was in the very inside?
Some white stuff.
Yes, some white frosting or something in there, right? So that was supposed to mimic the nucleus, and inside the nucleus was the proton. I went to Quick Trip just to get these. But I didn't tell my daughter to not eat them yet. So imagine that was still here. That's what I want you to put as far as the demo visual, just in Hostess cupcakes, and they've got that frosting on the very inside. That would be like the nucleus. I'm gonna put a link in for you to see what the gold foil experiment was like. What is his major contribution? Right here. He discovers the nucleus and eventually the proton. So nucleus and proton. And this becomes a little bit more like a model we're used to seeing when we see the atom. Is this all of this in the way? I kind of forgot about it. Well, you can stand up.
Mm-mm.
I won't kill you. Okay, is that better, Princess?
Yeah.
Okay.
Well, I'm not the one who needs to look at it.
All right. So with his model, right here we would say is the nucleus that houses the proton, and then outside of that is the electron. And he thought that the electron orbited the nucleus, just like how the moon orbits the earth or earth orbits the sun. And so that's why we see kind of these circles to try and show that they're orbiting. So same idea. Now what you maybe would do, oh Lord, can you make it look over here? What I think I would suggest for you guys to add in here, because I want you to realize that it's just the proton. He didn't recognize the neutron. So draw just a couple of separate circles to represent the nucleus. And then we'll draw like a negative here and a negative charge here as well. So these would be the electrons. This would be a proton. And then this whole thing would be the nucleus. And that would be the end of his model. He did not know that there was such a thing as a neutron, okay? Now moving on. So I will show that video link later for you to look at. Chadwick, he's our last guy, and we're gonna do his contribution first. So in the contribution column, he discovers the neutron. And think about why it probably was one of the last ones to be found. It's neutral, right? Protons positive, electrons negative, this one's neutral. And if we were to draw his model, now that looks a little messy, but the biggest thing to catch is in the nucleus, we now are showing two different subatomic particles. So if we go back to this, we could maybe have something going on like this, where you have your protons and your neutrons. and that thing is still called the nucleus, and then surrounding it would still be the electron. So for a demo, just think, I can't even really think of a good demo for this other than ghost mode. This would be like when you guys on Snapchat put your little people on the map on ghost mode and we can't find you. Just like how we can't find the neutron. It's vaporized, it's gone. We know it's there. Like I know that you're still there whenever you guys go on ghost mode. You didn't like totally disappear. I'm just having a hard time finding you because you're not showing up on the map anymore. And that's why the neutron was so hard to find as well. She's laughing at me in the background. That's the only thing I can think of right now. Okay. So where are we at with time?
20 minutes and your phone's
Holy
at
crap.
like
That, I think we're
5%.
gonna stop there. Like that's gonna be good or you guys are gonna kill me. I'm gonna have to let Miss Marcus know that there's just no way that we're gonna do more than that. 20 minutes is good. I'm gonna send those video links in there and we'll kind of move on from there with our next lesson. All right? Okay, you guys take care. Peace out. See you soon.
Peace out.
Tush.